Our last speaker today is now David Neufeld, molecular astrophysics with the Spitzer Space Telescope. David.
Okay. Well, thank you very much, and I'd really like to start by thanking Kate and the other organizers for the invitation to speak here. I'm really very honored to have been invited to do so. I'm realizing that when you're the last speaker at a wonderful symposium such as this one, it's really very difficult to add anything to the integrated wisdom of the previous speakers. And I think this is particularly true after Neil Lane's marvelous speech yesterday evening, which for me, I think really captured, almost everything that I believe about Alex. Still, I would like to make a few brief personal comments about what for me are the very most important one or two of the Dalgarno's laws that Neil enumerated. I was a graduate student with Alex in the mid-'80s from 1983 to 1987, and it was a very happy period for me in which I learned a great deal of science from Alex, starting with the inspiring atomic and molecular processes course that Amiel mentioned. Actually, I think it was the same course that Amiel took. If Alex is my academic father, then Amiel is my academic brother, and since he graduated a year before me, he's my slightly older brother. And perhaps in the manner of older brothers, Amiel was trying to convince me last night after dinner that the course that he took with Alan Porter as an undergraduate was a more advanced version of the course that I took as a graduate student. And I really have no way of knowing if this is true or not. But perhaps it's irrelevant because when I look back on this, of course, most of what I learned from Alex was not in class. And in fact, the more I think about it, the more I realize that most of what I learned, that I learned much more than science from Alex. And what I learned when I was here, just by observing Alex, and perhaps even without even realizing it at the time, was the right way, the moral way to behave as a scientist and a professor. And it's something that I've tried, however imperfectly, to carry with me in my own professional career. Of course, the right way is not always the easy way, and we all know that it's not always the path that is followed. So on the science side, I observed what it means to act with the utmost scientific integrity and intellectual honesty. And I had many questions for Alex during my thesis work. And of course, Alex usually had the answer at his fingertips, or amazingly would work out the answer in real time. But sometimes he would say he wasn't sure, or I don't know, or let me back off what I just said a little bit. And as you can imagine, it makes a great impression on an aspiring young scientist when a scientist of Alex's stature says he's unsure of something, because it allows you to say, I don't know. And of course, as a beginning graduate student, you have to say that a lot. And of course, I don't know, sort of the three little words that are what make science possible. On the mentoring side, I observed how Alex treated everyone, even the most junior scientist, with fairness and respect and great generosity and encouragement. And you take things for granted until you leave the nest and you find that this is not so everywhere. And I began to notice at scientific meetings, for example, just take one example, there are some senior scientists in the field who are really only interested in talking to other scientists who they thought were important or influential. And Alex, on the other hand, was always perhaps the most eager to speak to junior scientists and find out what they were working on. Alex said last night that he thought his most important legacy was the students and postdocs that he had mentored. And we, the former students and postdocs, may not necessarily accept that. We may tend to think more of the scientific breakthroughs and the seminal papers and the citations that resulted. But it's clear to me that Alex truly meant what he said last night, and that he's acted accordingly throughout his career. And that's really been to all of our great advantage, and is something for which we are very grateful. Thank you, Alex. What I wanted to talk today about was molecular astrophysics with the Spitzer Space Telescope, which is the fourth of the and last of the great observatories that NASA has launched over the last 2 decades. And in particular, I would like to emphasize molecules in astrophysical shocks. So I guess this is only appropriate after Evina has identified me as one of Dalgarno's hot guys that I should talk about shocks. It was certainly a subject that I've been interested in on and off since Alex first introduced me to this topic, which was the subject of my thesis. So in my introduction, I'll discuss the molecular origins of shock waves, the astrophysical origins of shock waves, and then I'll go on and talk about the power of the Spitzer Space Telescope for molecular astrophysics. And then I'll go on and talk about Spitzer observations of 4 simple molecules, interstellar hydrides, and of course all of which are molecules that Alex has focused on in his career. And they are molecular hydrogen, hydrogen deuteride, water vapor, and the hydroxyl radical. I'd like to acknowledge my collaborators on the work that I'll be describing, and in particular draw attention to Paul Sonnentruger, who's an associate research scientist at Johns Hopkins, and Yuan, who's a third-year graduate student. So what's the origin of shock waves in interstellar space? Why are they important? Well, it really comes down to the first 2 lines on this view graph. Basically, the sound speed in the cold interstellar medium is just a few tenths of a kilometer per second, and the Alfvén speed is maybe 2 kilometers per second. And there are many processes in astrophysics that can give rise to motions that are faster than this. And 3 key processes, all related to stellar birth or death, can lead to shocks. The first, which I won't really discuss, is the infall of material as a star forms onto a protostellar disk. The second is derives from the fact that the formation of stars, in addition to involving infall, also gives rise to the outflow of material at supersonic velocities along the rotation axis of the forming star. And then when stars die, or massive stars die, they do so in a supernova explosion that can send shock waves traveling far, far into the interstellar medium. Shocks have a number of effects. The physical effects of shocks are to heat, accelerate, and compress the material through which they propagate, and raise the gas temperatures to several hundreds to 10,000 or even, in fact, millions of degrees. And these heating effects can give rise to chemical effects in molecular clouds. And shocks can sputter grain mantles, the icy coatings that cover the solid interstellar dust grains, and release material into the gas phase. They can also drive chemical reactions with activation energy barriers that would be negligibly slow at, let's say, the 10-degree temperatures of dark clouds, but can be rapid once the temperatures raise above a few hundred degrees. And fast shocks can lead to the destruction of molecules and the ionization of the resultant atoms. And in addition, they emit ultraviolet photons that can irradiate nearby molecular gas. The Spitzer Space Telescope gives us a new window on shocked regions in the interstellar gas. And in particular, there's a spectrometer, the IRS instrument, that provides coverage of the mid-infrared region from 5 to 37 microns with much higher sensitivity and somewhat better spatial resolution than has been possible with previous observatories such as ISO, the Infrared Space Observatory. And this spectral region provides us access to fine structure emissions from atoms and atomic ions, vibrational bands of molecules both in the gas phase and in ices, and the subject of what I'll discuss today, also pure rotational transitions of light molecules, of hydrides. And here I'll discuss the 4 molecules listed on this slide. So let's just orient ourselves by taking a look at one of the spectra that we've obtained with Spitzer. This is the spectrum of a supernova remnant, 3C391. And here in the shortest wavelength part of the spectrum, we see a spectrum dominated by molecular hydrogen, pure rotational transitions, with emission also from PAHs, polycyclic aromatic hydrocarbons, and a couple of fine structure lines. At longer wavelengths, this is the short high module as it's called on this instrument. Again, we see more fine structure lines, and again, the S2 and S1 pure rotational lines of H2. And then at the very longest wavelengths, these 2 panels are just the same with a different stretch. We see again fine structure lines, the lowest rotational transition of H2, the S0 line, and, well, perhaps hard to see from the back, but real, also emission from HD. With Spitzer, one has a long slit spectrograph, and you can drag that across the sky perpendicular to its length, and you can make a map of all these lines. And so you can compare the distribution of various emissions coming from different components of the gas. And this has proven very useful. There's also a camera on Spitzer called IRAC, and it just provides broadband images at 4 wavelengths from 3.6 to 8 microns. But the interesting thing is that in certain regions of the interstellar medium, these bands are dominated by emissions from H2. So the quadrupole pure rotational transitions that, of course, Alex has studied theoretically. And you can see that schematically in this figure. The black curve shows the actual spectrum of a supernova remnant that we've observed. And then the blue curves here are filter functions indicating the acceptance wavelength or the responsivity of the instrument in the various bands. And you can see that bands 3 and 4, the longest wavelength bands, are dominated by H2 lines that we've actually observed. And if we extrapolate with a model for the excitation, we find that bands 1 and 2 are similarly dominated by molecular hydrogen. So it's a real demonstration of the importance of the molecular component of the interstellar medium. And so one has, with the IRAC camera, these large and very sensitive maps of material, and all this emission, with the exception of the point sources, which are stars, all of this emission is from molecular hydrogen. And you can sort of prove that by comparing these maps with the broadband images to maps of the spectral lines that we obtained with the spectrograph. And here's the comparison, which I think is remarkably convincing. This is what we see with the camera, with the broadband images. And these are the spectral line maps, and they're virtually indistinguishable. In fact, the only difference is this point here, which is a star, an embedded star, that shows up in the broad filter, but obviously doesn't emit molecular hydrogen. So this also has proven a valuable tool for studying molecules. Okay, so let me now go on and discuss the specific studies that we've carried out, and I'll start with rotational lines of molecular hydrogen. And in essentially every source we've observed, we can measure the S0 through S7 pure rotational lines of molecular hydrogen, so the lowest 8 pure rotational lines. And one way of thinking about this that astronomers use is to plot a so-called rotational diagram in which we show the logarithm of the column density or the number of molecules in each state or each magnetic substate versus the energy of that state. So it's a log linear plot, and if you had gas in thermal equilibrium, of course you just get a straight line. It's the Boltzmann factor. But this is actually what we see. It's not a straight line, and so here is such a rotational diagram, the log linear plot, for 4 different supernova remnants that we observed. And there are a number of features that I'd like to point out. The first is that all of these curves are positively curved. And this must imply that the gas is not at a single temperature, but there's a distribution of temperatures. And we've found that it's possible to model this quite successfully, assuming a power law distribution of temperatures, where the amount of gas at temperature T, or between T and T plus dt, is a power law, and typically it goes to something like the temperature to the -4. So there's much more cold gas than hot gas. And the implication of this is that this gas, which we believe to be heated by interstellar shock waves, must be subject, in fact, to a variety of shocks at different velocities. The reason I say that is that if you have a shock at a particular velocity, it typically gives rise to gas that is pretty much characterized by a single temperature. Of course, that's not exactly true, but it's nearly true. And this profile showing the temperature being almost a top hat function in the shock comes from a very important paper on interstellar shocks by Drain, Roberge, and Dalgarno that was published in 1983, and which really elucidated the structure, both physical and chemical, of shocks propagating through a weakly ionized, magnetized medium, such as the interstellar medium, in which the ions and the neutrals are not perfectly coupled, but drift relative to each other. I should say at the same time, this subject was also being studied independently by Chernoff, Hollenbach, and McKee. Okay, so that's the first thing that we observe, the curvature indicating that there must be a mixture of shock velocities in what we're seeing. And in fact, the power law index here is consistent with what you would expect if you had a paraboloidal bow shock with the fastest velocities at the head of the shock, and then as one moves down the side, more oblique shocks giving rise to smaller shock velocities and smaller temperatures. Another critical thing that you'll see if you look closely is that there's a zigzag behavior here. And in particular, all the states of even J lie slightly above the curve defined by the states of odd J. And this means that the ortho to para ratio of this molecular hydrogen must be out of equilibrium. The temperatures needed to excite these states, the equilibrium value is 3. And so this zigzag behavior is telling us that the gas is out of equilibrium. And the interpretation that we have of this is that what we're really seeing is a relic of an earlier epoch when the gas was cooler and had reached equilibrium with an ortho to power ratio appropriate to much cooler gas. And in fact, the lowest ortho to power ratio that we see is in fact much less than 1, is only about 0.25. The uncertainty of the intensities is, pardon? Yeah, the very small error bars. So they would be, and notice also this is 5 orders of magnitude here. So the error bars are believed to be about 20 or 30%. So they're probably smaller than the squares. And those would be entirely systematic errors. I mean, the signal-to-noise ratio on these is very, very good. Another thing you'll notice is that the degree of the zigzag decreases as you go to states of higher J. I mean, it's particularly apparent here, where you're much further from equilibrium for the low J states than you are for the high J states. And the interpretation of this, we believe, is that the hotter gas that is giving rise to the high J states has more effectively equilibrated than the cooler gas. So the idea is the gas has been heated up only for a short period of time, relatively, and at higher temperatures, the author to power ratio can more nearly reach equilibrium in the available time than at lower temperatures. And this is exactly what we expect, because the dominant process of equilibration under these conditions is reactive collisions with hydrogen atoms, and that has a barrier of about 4,000 degrees. And in fact, that's entirely consistent with the way the degree of zigzag varies. So that's molecular hydrogen, some interesting physics, I think, and also, of course, in some sense, one has a clock here that tells you how long this gas has been warm. The second molecule I wanted to discuss was hydrogen deuterite, again, a subject that Alex has worked on extensively. And this we detected serendipitously in the molecular cloud IC443, where we saw the R3 and R4 transitions. And since then, we've, with additional data, obtained further detections in a number of other sources. I should say that in the particular case of the Orion molecular cloud, there had been observations of hydrogen deuteride with ISO, the Infrared Space Observatory. So here are some of the spectra. Some of them are not very convincing, and we've only described them as tentative detections. But here in IC443, we believe we have a pretty secure detection. This is R3, this is R4. This big line here actually is H2S0. And our confidence in these detections is greatly enhanced by the fact that we can map this feature that we said was HD, and we can ask, what does it look like? And clearly, its spatial distribution is very similar to that of the warm molecular hydrogen. So this certainly sort of rules out the possibility that there's some bad pixel on the spectrometer array that is giving us a spurious feature at the frequency of the HD. Well, what we've been looking at in these clouds are warm clouds, but which were very dense and primarily molecular, were well shielded from ultraviolet radiation. And so we can make the assumption that all of the deuterium in the gas phase is in the form of HD, and then if you make that assumption, then basically HD over H2, which we can measure, is just twice the cosmic abundance ratio of D to H in the gas. And the value that we get is really quite low. So this plot shows a large number of sight lines, and the D to H ratios determined along for atomic clouds by the FUSE ultraviolet instrument. And actually things are plotted as a function of distance from the sun. And the typical value close to the sun in atomic clouds is about 1.5 10 to the minus 5. And then when you get further from the sun outside the so-called local bubble that surrounds our solar system, you see a large dispersion in the D to H ratio observed with FUSE. And then you, at large distances, you typically see considerably smaller values. And the values that we've measured in molecular clouds, these blue points here, are sort of in line, perhaps even a bit lower than the abundances detected in the atomic interstellar medium at similar distances from the sun. So this is all rather puzzling, and in fact there's been an ongoing debate motivated mainly by FUSE observations as to why the abundance has the value that it does. So the first thing to say is that all the deuterium in the universe was made in the very beginning, in the Big Bang, in the first 3 minutes after the Big Bang. And since that time, the only thing that's happened is that deuterium has been destroyed by stars, a process that's called astration. And so, assuming that we understand cosmology very well, which we sort of think we do now because of WMAP, the initial value was something like 2.7 times 10 to the minus 5, and this is actually confirmed by observations at high redshift. And yet close to the sun we have a factor of 2 less than that, and close or further from the sun, and in the clouds that we've been observing with Spitzer, it's a factor of 4 or 5 less than that. And in fact, models for the destruction in stars are very hard-pressed to explain such a large decrease in the deuterium abundance. And so there's been a very interesting suggestion, in fact, first by Mike Durer, although more recently made more specific by Bruce Drain, who has suggested that, in fact, most of the deuterium in the interstellar gas might be on deuterated PAHs, and that, in fact, we're seeing the effects of depletion, that in the gas phase, we're left with a significant shortfall of deuterium because it's all in these large aromatic molecules. Another possibility that we've considered in the dense clouds is that, in fact, there could even be further depletion on ices like methanol ice, which are observed to show remarkable levels of deuteration, where the deuterated version with just one deuterium can actually be tens of % of undeutrated methanol. And in fact, they've even seen triply deuterated methanol. So it's a very interesting chemistry, obviously, that explains that. But for our purpose, it might be an additional source of deuterium removal from the gas phase. Okay. Well, let me go on to my third molecule, water vapor. Shocks lead to large velocities, actually, relative velocities between grains, particularly charged grains, and the gas. And this can lead to the sputtering, particularly of the more fragile, icy surfaces, icy coatings of the grains. And this is expected to release water vapor. So that's one reason why shocks might produce water vapor. Another reason is that chemical reactions, a series of hydrogen atom abstraction reactions with H2, would rapidly convert any atomic, or for that matter, molecular oxygen existing in the pre-existing gas, would convert it into water. And here again, from this critical paper of Drain, Roberge, and Dalgarno, is a prediction for the abundance of various oxygen-containing species as a function, as one moves through the shock. And so one starts out in this model with oxygen atoms, and then very rapidly they're converted into water. So enhanced water abundance have indeed been observed in shocked regions with the Infrared Space Observatory, where it's been detected by means of its far infrared line emission. And we've been able to do a little bit of this in the mid-infrared with Spitzer, because there are some mid-infrared rotational lines fall into the Spitzer bandpass. They're somewhat harder to detect, but here's some recent results with Gary Melnick, Volker Tolles, and Yuan showing the observations of the mid-infrared region of the spectrum, and then a sort of toy model showing the strength and location of various water lines. And there are definitely sort of some certain, I would say, identifications and some less certain identifications. So, and we can map these emissions just as we could for HD, and we find that the water emissions shown in the upper two panels now have broadly similar distributions to the distribution of warm molecular hydrogen. It's been rather hard to derive exactly how much water there is, and we really need additional observations from Herschel to pin this down to say better than an order of magnitude. But even with these uncertainties, we find abundances of water in these shocked regions that are 1,000 to 10,000 times larger than what has been observed in dark clouds with the submillimeter wave astronomy satellite. And so this could be sputtering of grain mantles, or it could be gas phase reactions. And one key to this may be to study the temperature dependence, how much water is there as a function of the temperature of the gas. And I think Herschel, again, with its wavelength coverage at longer wavelengths than Spitzer, will be very critical here. Well, let me close with a discussion of one other molecule, the hydroxyl radical. And let me start by describing an extremely spectacular spectrum that has been obtained by ItamP and his collaborators and recently published in AppJ Letters. And this spectrum, which I'll put up in a minute, shows molecular hydrogen, water, and HD, the molecules I've discussed before, together with a picket fence of OH rotational lines. And let's take a look at the spectrum from Achim's paper. And at first, well, one sees some strong lines, fine structure lines, some lines of molecular hydrogen, and then there seems to be a lot of noise here, which is a little disappointing, but actually it isn't noise, and Achim was clever enough to figure out that these were very high-lying rotational states of OH that did not appear in the standard catalogs. And in fact, these states originate, I think they extend to rotational quantum numbers of order 30 or even higher. So energies above the ground state equivalent to 30,000 degrees Kelvin. And we know that the gas in these regions is only perhaps 1,000 degrees. So it's a real puzzle as to how these states were excited. Interestingly, there are no vibrational transitions detected, at least at the sensitivity available. I should say this work didn't involve me at all, and this was work Achim did with John Black and Charlie Larder. Well, I became very interested in this, and there's the question of how these lines could be excited. And so the question is, could photodissociation of water possibly be the pumping mechanism? Could that leave OH in a high rotational state? We know that there's ultraviolet radiation in these shocks because we see lines such as the lines of neon-2 that require high shock velocities that would produce ultraviolet radiation. And in the interstellar medium, where molecules are exposed to ultraviolet starlight, the photodissociation is dominated by the first absorption band between about 140 and 190 nanometers. And if you look in the literature, you'll find that experiments show this to produce OH in excited states, but the rotational temperature is only between about 500 and 1,000 degrees. And this is obviously far too low to match the observations, which indicate a series of equally strong lines really extending out to energies 30,000 degrees above the ground state. But then, of course, we realize that the ultraviolet radiation emitted by shocks is not just starlight, and in fact it's dominated by lines, and in fact one of the lines that it's dominated by is the Lyman alpha line. And you can then ask what Lyman alpha photodissociation does, and there's this beautiful paper of experimental results. There have been subsequent papers and also theoretical results that confirm this, and they indicate that when you have Lyman alpha radiation, you get photodissociation in the second absorption band. And that produces water specifically with rotational quantum numbers between 30 and 50. And this is exactly what is needed to account for the observations, because the OH molecules are all created in these high rotational states, and then there'll be a cascade down, and you'll see all the states below 30 essentially equally strong. This experimental result was confirmed by other experiments, which also provided the key additional feature that the production of the ground vibrational state is strongly favored. Quantitatively, you can ask how effective would this pumping rate be? And actually, there's a simple argument that shows you that if photodissociation is the dominant destruction process for water, and you're in steady state, then this pumping mechanism from photodissociation of water must dominate collisional excitation of OH. And here's the argument: the pumping rate via this mechanism has to equal the water photodissociation rate. But that has to equal the water formation rate. And water is formed by collisions of OH and H2, by reactions of OH and H2. And so it's proportional to the product of their densities. But similarly, the collisional excitation rate for producing OH in excited rotational states would also be proportional to this product, N of OH, N of H2. And actually, the constant of proportionality is more or less the same at high temperature, but there's a very different Boltzmann factor, because for collisional excitation, you require a Boltzmann factor of something like e to the minus 30,000 over T, whereas the reaction of OH with H2 to make water, well, it's actually exothermic, and it has a barrier of about 2,000 degrees. So this one has to beat this one at those temperatures. And so this must be the dominant pumping mechanism. And in absolute terms as well, for reasonable assumptions about the intensity of the ultraviolet radiation field and the column density of the water, which is also observed, one derives a line intensity that is broadly consistent with the observations. But this certainly needs more work, and John Black is sort of leading the effort on that. So let me summarize. Infrared and submillimeter spectroscopy, I think, is a very powerful probe of astrophysical molecules. And specifically, I hope I've convinced you that Spitzer observations provide information of broad astrophysical interest and also reveal a wide variety of the fundamental molecular processes, many of which, of course, Alex has elucidated. And then, as Evina said, and also Amiel, I think the future for observations in this wavelength region and for this kind of science that we're interested in is really very bright, with Herschel upcoming, the ALMA ground-based radio interferometric array, the James Webb Space Telescope, which will observe in the mid-infrared, and SOFIA, the stratospheric observatory for infrared astronomy that will fly on an airplane. So with that, thank you very much.
This is a very interesting talk, and we have time for, since we're ahead of things, we have time for questions. Tom. John.
Indications of specifically radiation from Lyman alpha, for instance, and fluorescence from ultraviolet. Are there any other indications that Lyman alpha is specifically important, for instance, in the fluorescence of molecular hydrogen or any other molecular processes?
So you're asking in general or in these particular sources?
Well, in the shocks in particular. Yeah.
In shocks in particular. So there are, as you well know, some coincidences between Lyman alpha and lines actually out of excited vibrational states, V equal 2, I think J equal 5 and 6, in the Lyman and Werner bands. And they potentially, could have observable effects. To my knowledge, and I haven't followed this actually that much for a while, but to my knowledge, I don't think there's any hard evidence that that effect has been observed in interstellar shocks. But it would certainly be something to look for. But with hydrogen in the ground state, basically there are no coincidences where the Lyman alpha can pump. But maybe John has something more interesting to say about this. Do you want to? Well.
Evina.
Just to follow up on the beautiful work on the HH211, I should ask this question to Achim or John rather than to you. But what strikes me is indeed the very bright OH lines, but relatively little water lines in that same region, whereas in the disks that we see around the young stars, we see lots of the water lines and very little OH. So obviously the UV is controlling the balance between the water and the OH, but I wonder whether you know already a sort of a quantitative limit on sort of what the water-OH ratio is in these shocks and how that compares with the models.
So that's a question for Achim. What is the water to OH ratio in these shocks?
Determine that you really need a very good model because of the huge number of lines and all the excitation mechanisms. So John is mainly working on that. Is a preliminary model ready to explain the OH intensities of the water, of course, is to be built in the same model and model at the same time. At the moment, the answer is no.
Yeah, I should add that we have recently obtained observations of CO625 and 726 of many shocked regions with the APEX telescope and 650, 850 gigahertz array. And we see around many of these shocks not just the broad shocked line profiles of CO, but also narrow, warm CO, likely indicative also of photon heating. So I think this whole issue of the UV heating of the sort of the outflow wall cavities is going to be much more important than we thought before.
Right.
And this
Yeah,
is a beautiful illustration of it.
Yeah. And Evina has also brought up something that I sort of excluded, that are very exciting results coming from Spitzer, which I've sort of arbitrarily excluded from my talk, are actually on two classes of objects, the exoplanets, now recently observed in the secondary eclipse, and also some recent observations by Salik et al. And Najita and Carr of extremely high-lying rotational lines of OH and water as well that are believed to come from accretion disks around stars, the very inner regions of accretion disks. And then also observations of lower-lying water transitions that are believed to come from accretion shocks, these reported by Dan Watson and his collaborators, where material is crashing onto the accretion disk and being heated in shocks there. So this is obviously a very fragmentary picture of molecular astrophysics with Spitzer.
So you're saying that the paramagnetic converter that converts ortho to para hydrogen is H atoms.
Right.
And that's an extremely reasonable suggestion, almost inevitable. Commercially, it's connected to some very interesting commercial things, because if you make hydrogen and liquefy it, you get a 3-to-1 ratio.
Right.
And the heat of conversion is 20 times the heat of vaporization.
Right.
The normal time of conversion is 1,000 days, but it means that within only 1/20th of that, in a few months or so, you spontaneously convert enough ortho to para to vaporize the entire tank, which is very dangerous. So commercially, if you're making large quantities of liquid hydrogen, you always wring out the extra heat with a paramagnetic converter, some transition metal or something.
Right. So that's sort of the exact opposite effect, where you're cooling too quickly and you freeze in a high ratio. And here we're talking about the inverse thing, where we're heating too rapidly for the ortho-para ratio to keep up, and we freeze in a low ratio. But that's true, yeah.
But what happens in the molecular cloud when all the atomic hydrogen is gone?
When all the atomic hydrogen is
molecular, which is not paramagnetic.
Right. So basically, this mechanism that we propose, the reactive collisions with hydrogen, assumes that a certain fraction of the molecular hydrogen will have been dissociated. Actually, another source of atomic hydrogen in shocks that would be perhaps also sufficient for this process is if there's pre-existing atomic oxygen, then those hydrogen atom abstraction reactions I mentioned that make the water, each one of them makes a hydrogen atom. And so you can actually get 2 hydrogen atoms for every oxygen atom that you start with, and that's enough to explain the degree of ortho-para conversion.
I think it's all very reasonable. It's a very nice idea.
Right.
Any more questions? Bill?
Can these levels of OH be seen Can these levels of OH be seen in the radio by their lambda doubling transition?
Well, they haven't. There have been some. So the ground, the lowest rotational state, obviously, is well known, and there are some excited states that are. I think the first excited state has lambda doubling transitions that have also been observed. But I don't know of any observations of higher states, and I don't know actually if the frequencies are known to the required accuracy. Or maybe
it's very hard to see thermal OH emission. You can see OH in absorption, and you can see an amazing. I hope Jim Moran doesn't contradict me, but it's just hard to see thermal OH emission in those transitions.
Any last point? Yeah. Well, I want to thank you all very much for coming. And this will close the session and will close the scientific talks. It's been a wonderful meeting. Alex, do you have any final shots? The concert, that's right. Well, we're right on. I think we're right on time, and I hope Cesare is okay.
So I want to thank everyone for coming and contributing throughout this meeting. I think it's been a wonderful occasion. We've all enjoyed your 80th birthday celebration, Alex, and I hope you have too. You did.
Yeah.